The moment has arrived. Thus far, we've been using Keras, a high-level API for calling on TensorFlow in the background to build our deep neural networks. Well, now we're going to be using TensorFlow proper. And we'll see that it's a bit more involved. There are more subtleties that we need to be aware of. TensorFlow is based around the idea of building graphs to describe computations. It's a little bit of a different way of thinking about doing computation. So there are three broad TensorFlow steps. So the first is building a graph. So that could be, for example, designing the neural network architecture. The second step is to initialize a session. And then the third step is to send data in and out of the graph in the session to be doing our computation. So first, let's talk about building the graph. So in any kind of graph parlance, we have nodes and edges. So the edges are the arrows that flow between the nodes. And in TensorFlow, we call these edges tensors. So the tensors flow into operations, which are shown here outlined in brown ovals. So matrix multiplication and add are examples of operations. And in TensorFlow, these always perform some kind of computation. Ops or operations can take in 0 or more tensors, and they can output 0 or more tensors. The other major component to the graph is the tensors themselves. So these are the black arrows, the edges. These have to be defined, so they can be an array with one or often multiple dimensions. So for example, with the MNIST digits, this could be an array of numbers representing pixel darkness with the image dimensions of 28 high and 28 wide. For the Oxford flowers that we worked with later on in these live lessons, these could be an array of numbers representing pixel intensity with 3 dimensions, the 224 pixels by 224 pixels times 3 color channels. There are 2 different types of tensors. So one of those is variables, which I have highlighted in pink here. So variables are stateful. We want them to retain their state throughout multiple executions of the graph. So for example, we want to be learning our weights W or our biases B over multiple epochs, over multiple steps of stochastic gradient descent. The other kind of variable that we have is shown here in blue. So these are initially, when we build our graph, just placeholders. So we define a tensor to hold the place of data like inputs X or outputs Y that we will later feed into the session. So whatever kind of computation we're doing, and we're going to run through some examples, we're going to go through some really simple ones before getting into deep learning, we need to arrange the ops and the tensors in advance of doing that work. So I have an example here that may be familiar to you by this point. So we've talked a lot about doing matrix multiplication on weights times some input X and then adding the bias B. So that operation right here is represented here on the graph. So we have our weights matrix here, and that is a variable that will hold state over multiple iterations of TensorFlow, of the TensorFlow graph. And then we have our placeholder X, and both of those tensors feed into this matrix multiplication operation. So this part of the graph here represents this W dot product X term here in the equation. Then we have our variable B that feeds into the output of the matrix multiplication. We add them together, and that sums to Z. So in a way, all of this here is a TensorFlow graph representing Z. And then we could feed all of this further into another kind of operation. So we could feed this into a sigmoid operation to have a sigmoid neuron represented here. So then we have our output alpha from this graph. Or we could choose, instead of sigmoid, we could have tanh here as our operation. Or we could choose relu. So this is an example on the board. We're going to get into some more specifics, and with some data, you'll be able to understand this more concretely in a minute. After we've built our graph, we want to execute the graph within a session. The reason why we do that is to allow TensorFlow to optimize the calculation of the graphs across all of the devices that we have available. So the CPUs or the GPUs that we have available on our machine or on our cluster of machines. Third, we need to get information in and out of the session. So there are two things that we need to do that. To get data into the session, we use feeds. So feeds specify the concrete value that will fill placeholder tensors at graph execution time. Feeds are always Python dictionaries. So curly braces with commas separating tensor names. Fetches are the counterparty to feed, and fetches return outputs from the session. So fetches can be tensor names contained in a list, so square brackets, or tuple, round brackets, and those allow us to return whatever information we want out of the graph. So with this particular graph, we would be using a feed to fill in this placeholder x, and then we would be using fetches to retrieve our weight matrix W and our biases B at the end of graph execution. So to get a bit of an understanding of how TensorFlow works, we're going to start with some really simple examples here. We are going to build some really simple graphs. We're going to recapitulate these graphs in a moment, but before we get there, let's just do some simple addition and multiplication. That kind of simple operation is a little bit trickier than just in base NumPy, for example. But that's because we're going to have all this infrastructure of building the graph, initializing a session, getting data in and out of it. So I have this demo already made for you in first TensorFlow graphs here in this notebook. So you can work with that. We are going to build it from scratch here. So we're going to call this first TensorFlow graphs demo. And so we can give it a title as such. And as usual, we're going to need to load our dependencies. Might not even make that explicit anymore. You get the gist. And we're going to import TensorFlow, which we're doing separately for the first time. So that's always been running in the background when we call Keras, but now we're importing it explicitly. So we're going to do some simple arithmetic. We are going to create one x variable here as a placeholder. And TensorFlow is a typed language, so you have to indicate precisely what type of data are going to be in this placeholder. So it's going to be a single point precision number. So we specify that with TF float32. And we're going to have two x's that we're going to do operations with. So they're going to have the same parameters initially. So now that we've defined our placeholders, we can define some operations to do operations on the values that will be in those placeholder tensors. So let's create a sum operation. To do that, we're going to use the add op. And the add op, we're going to specify to add together whatever values we put into x1 and x2. then we're also going to have a product operation. And the product operation is similar, but we're going to use the multiply op supplied by TensorFlow. And it's just going to multiply x1 and x2. So now that we've defined our placeholder variables, and we have also defined the operations that are going to execute on those placeholders, we can initialize the session, and we do it like this. Anything that we want to execute within the graph, we do within the indented line. So if we want to have some result from our sum operation, we run the session, and we specify that we want to fetch the result of the sum op, and we're going to feed in a dictionary. So we're going to use curly braces. So we have this feed dictionary parameter to feed in our x values, and so we specify them individually. x1 is going to be 2.0, and x2 is going to be 0.5. And we can do the same thing for our product. So we're going to have something similar. We're going to have a product result of running the product operation, and we're going to feed in the same values. So x1 will be 2, x2 will be 0.5, and then shift enter to run that cell. So now the graph is executed. So we should hope that the result of summing together 2 and 0.5 will be 2.5. And then the result of taking the product of 2 and 0.5 should be 1, exactly. So there you go. There's some simple arithmetic. Now, it's pretty rare with TensorFlow that we're doing operations on single digits. So let's do some arithmetic on arrays just to give you a sense of how this works. Let's leave our placeholder tensors as they were. We're still just going to have x1 and x2, and those are single point precision digits. And we're going to leave our sum op the same, so it's an operation that's taking in both x1 and x2, and same thing for the product. So we'll leave those exactly as they were above. We're going to copy and paste this cell, so we'll run another session. But this time, for our sum operation and our product operation, we're going to feed in an array. So let's feed in an array of 2.0s of length 3. So we have this array now here in x1 of length 3. All of them are the number 2. And then for our x2, we're going to have half, 1, and 2 as the values in there. For our product, let's do something different just to see what happens. So in our x1, we'll have an array of 2 and 4. And for x2, let's just leave this as it was. Let's leave that as half. And then we run the session, and let's see what our results look like. So for our sum, we end up with a 3 by 1 array. So 2 plus half is 2.5, and 2 plus 1 is 3, and 2 plus 2 is 4. So pretty easy to see how the cell by cell summation happened there. And then for our product result, we halved each of the values in x1 because we specified that with x2. So 2 times 0.5 is 1, and 4 times 0.5 is 2. So pretty straightforward. So having done that, done these really simple graphs, now we're going to build a notebook to describe this graph that we whiteboarded over here. So this graph represents the computations for a neuron, or a layer of neurons, if we feed in an array. And so we're going to build that here now interactively. So I have already created this notebook for you. It's first TensorFlow neurons. You can follow along there, or you can follow as we build it here and describe what's happening. So we have our first TensorFlow neurons notebook. and we can title it as such. So we're going to need to load our dependencies as usual, and we're going to set the seed this time so that we have reproducibility, because we're going to have some otherwise random selection happening later on. And we're going to want to plot some of our results, so we're also going to import matplotlib. All right, so random seed. There we go. So the first thing that we're going to want to do is set our number of input neurons. So I'll say that here. And in our input layer, we're going to have a number that we're very familiar with now, 28 times 28, from our MNIST digits, which is 784. We're not actually going to be working with MNIST digits in this demo, but it's nice to have some familiar numbers around. And then we're going to specify that our one layer of dense neurons that we're building here is going to have 128 neurons in it. So then we need to define a placeholder tensor to hold our simulated MNIST digits. So we need to define tensor and we do that with the placeholder function here, just as we did in the last notebook. We're going to define those as single point precision numbers, and we're going to specify the shape. So we're going to specify it to be a one-dimensional array with length of 784. Now we're putting the 784 in the second position so that the array is aligned properly for our matrix multiplication later on. Now we also, in addition to defining the placeholder tensor, we need to define our variable tensors. So these are the tensors that are going to hold W and B. So B we can define with capital V variable, and we're going to start B off to just be zeros. So we're going to specify zeros here, and we want it to be an array of zeros that is in the right dimensions. So we're going to say it's of length 128. We define that above. And we also need to define our W matrix, our weight matrix. Now, we talked a little bit about initialization earlier in these lessons. So we might be aware that we could start with a random uniform distribution. But we know that the results aren't going to be amazing. But we're going to stick with that for now anyway, just so that I can show you what the results of starting with a poor initialization looks like. So we are going to sample matrix W to have n input rows, so 784 rows. We can actually define that up here too. We already defined 784. So we're going to have the same number of rows in W as we have length in the placeholder X. And then the number of columns in our weight matrix is n dense, which is the same as our biases here. So that way we can perform matrix operations in between all three of these. Now that we've defined our tensors, our variables W and B, as well as our placeholder X, we can start to define the computational graph. So we're going to start by defining Z here. So Z, as we can see in the diagram, is the result of matrix multiplication first. So we're doing matrix multiplication on X and W. And then we're going to add B to the result of that matrix multiplication. So we do that by adding to the result. So we're adding b to the result of multiplying x and w. So that defines this part of the graph. Now we also want to take the result of z, pass it through some function to create our neuron activations A. So to do that, we simply define some function. This could be sigmoid on our z, and we output that to A. So there we go. We've defined our computational graph. There's one little step that we haven't talked about yet, which is we need to initialize our variables. So we'll be doing this in all of our graphs from now on. So this initializer op, we'll always define it as a global variables initializer. And what this means is that in the next step, when we execute our session, this initializer operation takes all of the variables that we've created so far in the notebook, all of the tensors, and creates the computational graph appropriately. So that's just something that will always stay the same. And finally, we get to execute our graph. So just as we did in our last notebook, we're going to instantiate a session here as session. We're going to run the initializer op that we just defined, and then we can actually tell it to run the graph. So we're going to have some output from our layer output, and we do that within the session run. So we're going to fetch A, because that's the end result of all of this graph. So that's what we're going to fetch. And we need to feed in some data. We do that in a dictionary. So we can say our feed dict is equal to, so we're going to have, we'll define our dictionary as x. And we haven't actually, we're not loading in any MNIST digits. So we're going to randomly initialize x with values from the numpy random function here. And above, we said that our placeholder x was going to be of a one-dimensional array with length 784 and input. So we need to specify that again here. And voila, it runs. And we can have a look at our output. So because of the parameters that we initialized with, the output from our network is all ones, which isn't very informative, and it would be very difficult to learn weights with that. So let's have a look at the results. I'm just transposing them so that we can plot them with matplotlib. So obviously all of our values, all 128 of our values, are at 1. So this allows us to see the value of initializing properly. So we know that initializing with a random uniform distribution is not ideal. So another alternative would be to initialize with a normal distribution. So let's rerun our whole notebook now doing that. Now we see that we have a lot of different values being output. And those values, after they pass through the neuron, they end up being not zero-centered, but they tend to be at the lowest possible values, 0, or the highest possible values, 1. Once again, these are relatively difficult values for a neural network to be learning with. We'd like the output of any layer to be normally distributed. And so earlier we talked about using Xavier-Glorot's approach to initializing so that the outputs of a layer are normally distributed. To do that, we need to change around the way that we create this tensor a bit. So let's comment out this line. And we're going to define it now with the getVariable command. So within the getVariable command, we do things a little bit differently. The first parameter that we define is the same as the variable name. And then we are going to choose the same dimensions as we had with our previous initialization. And the critical step is that now we're going to use the initialization that we want. Which is the Xavier initializer. And there we go. So using Xavier initialization, when we execute the graph, our outputs from the neuron layer coming out of this graph will be nicely normally distributed. So that's a pretty cool property. And one last thing that I want to show you quickly is that we could define this neuron type to be any kind of activation. So the activations that we've talked about are sigmoid, tanh, and relu. So let's just have a quick look at that. We'll change sigmoid to tanh here and rerun all the cells. Remember that for the sigmoid, we had results from 0 to 1, as we'd expect. For the tanh neuron, our results should be from -1 to +1. And because of the Xavier initialization, they're still relatively normally distributed, as we'd hope. And then we can have a look at using the relu activation as well. Can run that quickly here. And the relu activation has a floor at 0 and then can go up to any possible value, but because of the clever Xavier initialization, most of those values aren't too far away from 0. So regardless of the activation that we're using in this neuron layer, whether it's sigmoid, tanh, or relu, when we use Xavier initialization, it gives us nice values coming out of this layer that are near 0 but not exactly 0, and so that's ideally suited for learning throughout our neural network.